So to have an intersection point, an intersection is when two lines cross. So an intersection is where two lines cross. So you graph a line, another line, and they cross at a single point. So whenever you're talking in terms of intersection, an intersection is just when two lines cross and they meet at a single point. Since we're in the topic of triangles, triangles have three sides and three angles, which means when triangle pieces cross and the segments within them, that's called a point of concurrency. So a point of concurrency is where three lines intersect or cross. So when we get to a triangle, you'll have 3 points crossing, or 3 lines crossing to form a point of concurrency. So an intersection is when 2 lines cross. A point of concurrency is when 3 lines cross. So we're going to be talking about points of concurrency today and the special segments within a triangle that make those points exist. So it's a lot of matching. All right? Yep, I told him about that day. Yeah, it's one of those days. So we're going to start with medians and a centroid. Right? So it's a lot of matching, segment to point, segment to point. Okay? And on page 40 has a chart that is going to make this a little bit easier and to help you match a little bit easier. So it's just about matching. So medians and the centroid. So let's first talk about what a median is. So a median is kind of like in the road, you know how they have like a concrete or some, I don't know, grass or something. It divides the road into 2 parts. One's going one direction, one's going the other direction. So the median cuts a road in half, and a median of a triangle cuts a side in half. So it's the same idea. So the term median is a segment connecting the vertex, which is the angle, so the vertex of a triangle.
Hey, this is all your class?
Yep. Stuck with me till you graduate or drop out. But I think you'll graduate, so I think we're good.
Third.
Huh?
I'll go for third.
Yeah.
I'll drop out in lunch.
Just the day before graduation, you're just like, I can't do it anymore. Yeah. You're stuck with me.
Well, you see that mill or something?
Huh?
You see that mill or
What?
you see the mill? You come in the mail.
Oh, in the mail. Sorry, I'm having like the worst time hearing. I think you get your diploma at graduation unless you owe fees and fines or you have to do credit recovery. Then you have to do stuff in the summer and then you get it. But if you don't go to graduation, then they mail it to you.
What would be on this year?
I think we'll do graduation, so you'll get it at graduation. If we did it last year, we'll probably do it this year. Outside again. So the median is a segment connecting the vertex of a triangle to the midpoint of its opposite side. So whenever you're dealing with medians, they have to start at the vertex angle, which is A, B, or C. They will connect to the midpoints of the sides. Now these are different than mid-segments because they're not parallel. So if we started A would connect down to F. That is a median. Medians cut sides in half, which means F is a midpoint.
No question.
Yes. D and E, no, we're not going to draw a mid-segment. We're going to start at the angle and go to a side. So it's a little bit different from mid-segment. Yeah. Okay. If we had a median drawn with a mid-segment, yes, there would be a point in the middle. But in this case, we're only going from the angle to the side, so we're not going to draw a mid-segment. So then we're going to start at B. B is going to connect to E, and E is going to make a midpoint of AC. So this gets 2 bars on each because E is the middle. And you do the same thing from C to D. at 3 bars. Now, in the picture, the actual mid-segment itself, okay,
The right one. Under what 2 minutes ago on the when D and B under 3.
oh,
Yeah, we're saying second E and C and D. So 2 and 3.
yeah, 2,
Down with the
okay. So the median is a segment. So in this picture, A to F, B to E, C to D. That is the segment. And it connects the midpoints, which in this picture are D, E, and F.
that point on that one point in the middle.
Yes, that point in the middle is called the centroid.
Oh, we're gonna give it a letter.
Yeah, we're gonna give it a letter in just a second. Okay. So the segments start at the angles and go to a side. And the midpoints are going to be on the actual sides of the triangle. Now the centroid is that point where all of those medians crossed. So we've got that intersection point kind of in the center of our circle, or of our triangle. That's called the centroid. So this piece right here we're going to call G as an intersection point. That point is called the centroid. So the centroid, by definition, is the point of concurrency. And remember, it's point of concurrency because we have 3 lines crossing to make that point. So it's the point of concurrency of the medians in a triangle. So the term centroid, think center, it's kind of like the balancing point of a triangle. So if you were to balance at the centroid on your finger, that triangle that's created, that would balance the triangle evenly. So the centroid is referred to as the balancing point of a triangle. It's a key word. It's the balancing point of a triangle. Okay. Now, the segment for the centroid. So in our picture, G is our centroid piece. That's called the centroid. That intersection piece, that point of concurrency, creates some, segment lengths that require us to understand some fractions. So it breaks that segment into pieces. Okay. As far as us remembering all the formulas, you don't have to. Okay. But you do need to kind of understand how the centroid breaks up a median. So I'm going to redraw AF. So I'm going to put A, go down 2, put G, go down 1, put F. So what we're actually doing is kind of mimicking the median AF. By drawing it 2 blocks and 1 block, we're going to be able to represent our equation a little bit easier. Okay. So for our equation, the distance from A to G is 2/3 of A to F. Okay. Now, as far as us memorizing this equation and using it, as long as you can identify it, you're good. So the distance from the vertex angle to the centroid is 2/3 of G to F. So if we were going to clear that fraction, we'd multiply both sides by 3 and distribute the 2. Okay. But again, you don't have to memorize all of that. This is just saying the distance from the vertex to the centroid is 2/3 of this to this. The key takeaways for medians is that the medians cross at a centroid. The centroid is called the balancing point. And that's it. It's all about identification. All right. Our next one is angle bisector and the incenter. Okay. So medians divide sides into equal pieces. Okay. Angle bisectors is going to be a term from your 11th grade year, whenever you learned about angle bisectors, perpendicular bisectors, midpoint, all that stuff, okay? So what does an angle bisector do? Or a segment bisector, what does a bisector do? Okay, so by it bisecting the angle, what do you mean when you say bisect? Splits it in half, is that what you said? Yeah. So an angle bisector splits an angle in half. Angle bisectors have to go from the angle to the side. Okay? They have to go from the angle to the side. So we're going to draw the best we can. Okay. This angle down to about here. Okay. Yeah, a little bit to the left of A. And what that's done is it's dividing this angle into two equal parts. So that's an angle bisector. Okay. Yeah, B is going to kind of end about here. So you connect it, and it's not going to be perfect. We don't have protractors. So once you make two of them cross, you at least have an intersection, which means when you go from C, go through that intersection. So it's going to look something like this. So on start, and kind of continue. It's hard to do without a protractor, but just do the best you can. It should cross at a point. So angle bisectors, what they do is they cut angles in half. So angle bisectors, it is a ray in a triangle that bisects an angle and goes through the opposite side. So an angle bisector has to start at an angle because it's cutting an angle in half. It's going to go through the opposite side. It doesn't cut the side in half. Okay, it's not a median. It's a bisector for angles. So it has to start at an angle. It's going to go through the opposite side, but just not go through the middle. Okay. So in our picture, our angle bisector is represented by all of these lines. The key for an angle bisector is that it cuts the angle in half. That's what it does. Okay. So an angle bisector starts at the angle, cuts the angles in half, and all of those lines cross at that point. That point is called the incenter. So angle bisectors, when they cross at a point called the incenter. It's all about matching. It's matching segment names to points of concurrency names. So in our picture, this point right here is our incenter. So the definition for incenter is the point of concurrency for angle bisectors. An incenter is where the angle bisectors cross. Of concurrency of the angle bisectors. And I'm using the symbol for angle so we get practice using it. If you want to write the word angle, you can. But the incenter is where the angle bisectors cross. Now, the incenter has a special property whenever it's drawn inside of a circle. Again, it's going to be hard to draw free-handed because we're going to have to draw a circle free-handed. It's easier with a protractor and a compass, but we're not going to get into all that. It's just a sketch. All right, so to draw this, I'm going to start at C, count 3 units left and 2 units up, and put a dot. That dot is going to represent the in-center. Again, we're freehanding this circle. It's not going to be the best. It will be the best? Okay. I'm going to draw it in pencil because I don't trust myself to draw it right. What we're going to do is draw a circle inside of this triangle. So that kind of is going to touch part of the triangle. Mine is going to look more oval-esque. Basically, it's just a circle. Try your best. It's just a sketch. Doesn't have to be perfect unless you're Gabe and it has to be perfect. How perfect is yours, Gabe? Does it look good? So the in-center, when you draw it, you can actually create a circle inside of the triangle. And that's one of the key identifiers to an in-center. It's all about matching terms. Okay. So the way that we're going to match this is if I draw a segment from the in-center to the point on the circle where it touches, I've created equal radii. Now I know we haven't gotten to circles yet, but a radius is a segment that goes from the center to a point on a circle. It's a term you've heard before. So everywhere that circle touches, it makes it a radius. The radius is also going to be 90 degrees, so I'm going to put some 90 degrees here. Whenever you have an in-center, you might see this picture on the bottom. So you've got a circle inside of a triangle, that's the in-center. So to describe this picture, using the in-center, a circle can be constructed. That looks like an E. A circle can be constructed inside a triangle.
Don't put a square in there if you want to.
Yeah, we could draw a square, but whenever you have the 3 sides, it's going to make more of a triangle inside. But yes, a square could fit in there, but it doesn't really have a matching piece with the in-center. So anytime you have an in-center, a circle is going to be inside of the triangle. Think in-center, inside, circle inside. Again, I know that these words are weird. I know that you probably haven't seen the word centroid or in-center. It's just some new vocabulary mixed with old vocabulary. It's all about matching. Okay, it's all about matching. So an in-center creates a circle inside of a triangle. So this little point right here, that's the in-center. So median goes with centroid. In-center goes with angle bisector. It's all about matching. Okay. I'll give you a second to get caught up. Okay. It's all about matching. So we've got 2 more special points of concurrency to go. And then we'll do our little chart to kind of put them all together. I know that this is a lot of vocabulary, a lot of reading, not much math. Kind of feels like English. All right. The term altitude, you might not have heard before, but to relate it to your real life, okay? If you go on an airplane, or if you climb a mountain, altitude is how high above the ground you are. Now, an altitude in a triangle, its special property is that it makes 90 degrees with the opposite side. Altitude is 90. Now, the other two theorems that we talked about are medians and our angle bisectors. They're always inside the triangle. Altitude, however, moves around depending on what kind of triangle you have. So let's define altitude first. Altitude is a segment in a triangle that goes through the vertex angle and makes 90 degrees with the opposite side. Ran out of room there. So depending on the type of triangle, the altitude might go outside of the triangle. Because the altitude's main goal is to make 90 degrees. That's its only purpose. Start at a vertex angle and meet another side, make 90 degrees. That's all it does. And doesn't cut a side in half. It doesn't do pretty much anything else other than 90 degrees. Now, depending on what type of triangle it is, the orthocenter, which is the point of concurrency, moves around. Okay? So the orthocenter, I'll do that definition below it, to kind of point into its space. It is the point of concurrency of the altitudes. The orthocenter moves depending on the triangle type. Depending on the type of triangle, the location of the point moves. And so the altitude goes from the vertex angle to the opposite side and makes 90 degrees. The orthocenter is where all of the altitudes cross. The orthocenter will move. It's not always going to be inside of the triangle, like the centroid or the incenter. It moves around. Okay. So in an acute triangle, our orthocenter is always going to be inside. So looking at our picture, our altitudes are here, here, and here. They make 90 degrees with the opposite side. That's all the orthocenter, or the altitudes do. Now, since the altitudes are in an acute triangle, meaning all our angles are less than 90, since they're in an acute triangle, the orthocenter will be located inside. So in our picture here, our orthocenter is here. So if the triangle is acute, the orthocenter is inside. I know that kind of looks orange. Okay, but in this case, it's inside. So I'm going to use the same color I used for orthocenter. So the orthocenter is located inside of the triangle. Again, it's a lot of vocab. It's a lot to kind of learn in one day. That's why we're going to do some IXL to make it a little easier. It's all about identifying. Okay. This will help us later on too if we can read a picture. Okay. It makes challenging topics just a little bit easier. Now on a right triangle, the altitudes actually cross at the 90-degree angle of a right triangle. So in this picture, AC, BC, and this segment actually cross at point C. Point C is where the orthocenter is if the triangle is right. So if it's a right triangle, it's on the 90-degree angle. Orthocenters can be a little weird because they can move. They're not always inside, right in the center. Depending on the type of triangle, it moves around. So if the triangle is a right triangle, the orthocenter is located on the 90-degree angle. Okay. If the triangle is obtuse, the orthocenter meets outside of the triangle. So in order for this angle to make 90 degrees with the side, you have to extend this side out. So what that ends up doing is creating altitudes. I think I drew that wrong. It's fine. I think I connected one point wrong. It's fine. It's not a big deal. So the orthocenter is here, outside of the triangle. No, I did it right. I did it wrong in my old notes. I was just kidding. All right. So if the triangle is obtuse, the orthocenter is outside. So think obtuse starts with an O, outside starts with an O. So this is outside the triangle. All right. So depending on the type of triangle, the orthocenter moves around. Again, our chart on page 40 is going to make this a lot easier. Kind of see, make comparisons amongst everything. Altitudes make 90 degrees with the side. That is their main goal. They're going to cross outside of a triangle. All right, let's hop to page 40. We're going to do the very last one before we do our chart and do the IXL on matching. Okay. I'll give you a second to finish copying. Like 8:40. Oh, I'll do lunch count in just a second. Yeah, whenever we're done with. Oh, we'll do IXL here in a minute. All right, let's try the next one. The very last one is the perpendicular bisectors. Okay. Again, a lot of matching. A lot of things happen with these segments. It's mostly just identifying. That's it. It's a lot of vocabulary. All right. A perpendicular bisector you've learned before in your first class of geometry. A perpendicular bisector goes through a side, makes 90 degrees, and goes through the middle. So it does two things. A perpendicular bisector intersects a side of a triangle. Makes 90 degrees with the side, with the opposite side, we'll say, and it goes through the midpoint. So perpendicular bisectors, they intersect with the side of the triangle, make 90 degrees with the opposite side, and go through the midpoint. They do a lot of stuff. Just like the orthocenter and the altitude, it moves around. The intersection point between all three of those lines, it moves, depending on the type of triangle. So the circumcenter is the point of intersection of all the perpendicular bisectors. So before we move to our pictures, the circumcenter is the point of concurrency of the perpendicular bisectors. Depending on the type of triangle, the location of the circumcenter moves around. Just depends on what kind of triangle it is. Okay. So if it's acute, the point of concurrency, the circumcenter, will be inside of the triangle. If it's acute, the point's always inside. So the acute piece, our perpendicular bisectors are located here. Notice how they don't have to start at the vertex angle. They don't have to start at an angle. Their goal is to make 90 degrees with the side and cut it in half. So it can't always start at an angle, and that's okay. Notice in your pictures how you have the 90-degree box and congruent segments, which show perpendicular bisectors. Now, the circumcenter is located inside if the triangle is acute. So it's inside the triangle if it's acute. Any acute triangle, it's always inside. If the triangle is a right triangle, it's going to be on the hypotenuse. So the point of concurrency, the circumcenter, will be located on the hypotenuse if the triangle is right. So if I trace out these segments here, here, and here, notice how they cross on the hypotenuse. A lot of stuff happens with points of concurrency. That's why at the end we're going to make that chart, kind of put it all together, make it a little bit easier to identify. So on a right triangle, it's always going to be on the hypotenuse. Okay. If it's obtuse, then it's outside. Obtuse, outside. So if we connect all these perpendicular bisectors, they cross outside. Again, this point moves around just like the other one. It's just a lot of reading a picture, making sure you understand the picture, kind of matching. It's a lot of matching. We'll spend a bunch of time practicing the matching, making sure that we can go back and forth between segment and point, picture and segment. Okay. Now, the circumcenter has a special trait involving circles. Okay. So to start, we're going to freehand a circle. Okay, we're going to freehand a circle right here. I should probably do it in pencil first because I'm not the best. Yeah, I'm going to put underneath where it says special trait, I'm going to try to draw a circle. Because what we're going to do is put a triangle in it. Yeah.
Why is there a apartment in the middle? Besides the frame?
Why is there what in the middle of this dot?
Yeah.
Because when I was handwriting it, I messed up. And I whited it out. So you can see all of my mistakes on these papers. Yeah, there's some white on page 39 too. You know, don't judge me. So we got our circle. Now inside of the circle, we're going to draw a triangle, and I'm going to draw an acute triangle just to make it a little easier to draw. So to draw it, I'm going to start here, down, go over. Again, it's not perfect. It's just a sketch. Doesn't have to be amazing. What happens is whenever we have a triangle and we have the circumcenter as the point, if we were to draw, so if I go back into this acute triangle, if I were to draw a circle, I could draw a circle that touches A, B, and C. And that's basically what we were kind of doing here. The circumcenter kind of acts as the center of the circle, creating radii, which means the radii are going to be equal measure going to the side. So these points, when we're talking with triangles, they have special traits. And they've got special traits. They make special pieces. Things happen with them. In a circumcenter, you can actually draw a circle outside of the triangle. So I've kind of run out of room. I'm just going to write it here. Its special trait is that a circle can be drawn outside the triangle. So what happens is I have this triangle. A circle has now been created around it. Circle can be drawn outside. So those are all 4 of your new vocabulary words. It's a lot. I know it's a lot. You're learning a lot of new vocabulary words at the same time. A lot of stuff's happening. So for its special trait with the circumcenter, a circle can be drawn outside of the triangle. Since a lot of these vocabulary words are based on identifying, if you can recognize a circle outside of a triangle, you'll know immediately that it's a circumcenter, just based on the vocabulary alone. All right, so the chart. The chart involves all of the vocabulary words, all of the pictures that we learned on the previous pages. It's just kind of combining everything together. So let's first define median. What is a median? You don't remember? Look on page 39. Okay. It's a segment that starts at the vertex and bisects the side, goes through the midpoint. So the median's main purpose is that it bisects a side. The other important part is that it starts at the vertex. Not all of these segments start at a vertex. So the main important part of a median is that it bisects the side and it has to start at the vertex angle. It's got to start at one of the corners of the triangle. When all of the medians cross, what is the point of concurrency called? The centroid. Good, the centroid. So when all the medians cross, they cross at the point called the centroid. The centroid is also referred to as what kind of point? It's on the page. What kind of point is the centroid called? The balancing point. Good. So you might see the balancing point on a problem, and that would just refer to the centroid. Where is the centroid always located inside of a triangle? Or I guess I just told you where it is. So the point of concurrency, if it's a centroid, is always inside. There we go. That's fine. Should have pre-wrote my questions. So it's always inside the triangle. You can't have a balancing point of a triangle if it's outside of the triangle. So the centroid is the point where all of the medians cross, and it is always inside of the triangle. All right, altitude. What does an altitude do? What does an altitude do? Perfect. It makes 90 degrees with the side. That's its main purpose. And altitude must also always start at a vertex angle. Always has to start at a vertex angle. So anytime you're dealing with an altitude, it's going to make 90 degrees with the side. It will always start at one of the vertex angles of the triangle, like A, B, or C. 90 degrees starts at a vertex angle. All right, what is the point of concurrency that corresponds to altitude? Orthocenter. Altitude goes with orthocenter. When all those points cross, it's called an orthocenter. All right, what about location? Is the orthocenter always inside of a triangle? No, it can move around, so let's start with acute. If the triangle is acute, where is it located? Inside. We've got a right triangle. Where is it located? On the 90 degree. If it's obtuse, yes, always outside. The best way to kind of remember these, think O, outside, obtuse. Okay? Orthocenter, outside, obtuse. If it's right, it's on the 90 degree angle. If it's acute, it's inside. So this one kind of moves around. All right, perpendicular bisector. What does that do? What is a perpendicular bisector? Mm-hmm. It does what? Say it again. Okay, there's like two sides of a triangle. What else does it do? Make any certain measure? Yes, 90 degrees at the opposite side. So this makes 90 degrees with the side and goes through the midpoint. The perpendicular bisector. The perpendicular bisector, it does not have to start at a vertex angle. This one doesn't always start at a vertex angle. It can on one type of triangle, but it doesn't always have to, because its main goal is to make 90 degrees with the side and cut that side in half. So it doesn't have to start at a vertex angle. What is the point of intersection called? The point of concurrency. Perpendicular bisector. Circumcenter. Now, circumcenter has a special trait. How can the circle be drawn? Where's the circle located? Outside of a triangle. So, circumcenter, if I draw a circle and a triangle inside of that circle, the circumcenter will make a triangle or a circle outside. So being able to match is important. The circumcenter is equidistant, which just means equal distant. Equidistant to the vertex. So what that means is, if I start at the circumcenter, I can draw a segment from here to the vertex angle, and it's going to be equal all the way around. Makes a circle outside. Where's the location of the circumcenter? Is it always inside? No, this one moves around as well. So if the triangle is acute, where is it? Inside. A right triangle. Good. Right triangle is on the hypotenuse. Obtuse? Yes, outside. Forgot how to spell this. I know it's a lot of matching. It's a lot of words. It's going to take time to kind of tell the difference based on pictures, so that's okay. Our last one is an angle bisector. What does an angle bisector do? Bisects the vertex angle.
Ideal would be plus.
What?
If I knew, it would be plus.
I don't know what you're saying.
If I knew, it would be plus.
If you knew what an angle bisector was.
Oh. Good. Okay. I don't know how to respond to that. I'm not quick. I'm not feeling that great today, so I'm not as quick-witted as I normally am. So we'll just let it go. All right. It bisects a vertex angle. The thing about angle bisectors is that they have to start at a vertex angle. So it starts at a vertex angle. The only one that doesn't have to start at a vertex angle is a perpendicular bisector. All the other ones have to start at one of those main angles. The angle bisector is called an incenter. So all of them cross at what's called an incenter, and the circle is located inside of the triangle. So I'm going to draw a right triangle over here. Our goal is to freehand a little tiny circle in there. So, close enough. What happens with that circle is that the in-center distance to the side is always equal. So the in-center, if I'm going to the side of the triangle, it's equal. So this is equidistant to the sides. Where's the in-center located? Yeah, it's always inside. So we've kind of narrowed it down. Page 40 is going to be the most help because page 40 has all the information about everything we learned.